Welcome to this coding walkthrough. In today's session, we'll explore LeetCode problem number 1786, titled Number of Restricted Paths from First to Last Node. This problem challenges us to work with weighted, undirected graphs and calculate the number of restricted paths between specific nodes. Let's dive in and break it down step by step. In this problem, we are working with a weighted, undirected graph that has n nodes, numbered from 1 to n. The graph is defined by an array of edges, where each edge connects two nodes u and v with a specific weight. Now, the goal is to determine the number of restricted paths between the first node and the last node, or a restricted path must meet a specific condition. For every pair of adjacent nodes, u, v, in the path, the shortest distance from v to the last node n must be strictly less than the shortest distance from u to the last node. Essentially, as we move along the path, the distance to the last node must consistently decrease. Since the number of such paths can be very large, we'll return the result modulo 10⁻9 plus 7. The graph is guaranteed to be connected, so we know there is at least one path between any two nodes. The output of the problem is a single integer, representing the total number of restricted paths from node 1 to node n, modulo 10⁻9 plus 7. Let's look at an example to better understand. If n is 5 and the edges are defined as shown, there are three restricted paths from node 1 to node 5. The first path is 1-2-5, where the shortest distance from node 2 to node 5 is less than the shortest distance from node 1 to node 5. Similarly, the second path is 1-3-5, and the third path is 1-4-5. In each case, the distances decrease as you move closer to node 5. This illustrates how the condition for restricted paths is satisfied. Now, take another example where n equals 2 and the edges are just 1, 2, 3. Here, there is only one restricted path, which is the direct path 1-2. Since there's only one edge, the condition is naturally satisfied, and the output is 1. These examples demonstrate how restricted paths are identified based on the distances between adjacent nodes. The constraints of the problem also ensure that the graph can be quite large, with up to 2*10⁻4 nodes and 5*10⁻4 edges, so the solution must be efficient enough to handle these limits. The weights of the edges can be as large as 10⁻5, and the graph is guaranteed to be connected. There are also several important edge cases to consider. For instance, with the minimum possible input of n equals 2 and a single edge, the solution must return exactly one restricted path if it exists. For a large graph with the maximum constraints, the algorithm must ensure it remains efficient. Another scenario to handle is when all nodes are directly connected to the last node n. In this case, the solution must still validate that the paths satisfy the decreasing distance condition. Additionally, if there are multiple shortest paths between nodes, the algorithm should handle these ties correctly and count all valid restricted paths. These considerations help ensure the solution is both correct and optimized for all possible inputs. To solve the problem of finding the number of restricted paths in a weighted, undirected graph, we first need to understand the nature of these paths. A restricted path is one where the distance to the last node, node n, decreases strictly at every step along the path. This makes the problem challenging because we need to account for both the graph's structure and the distance constraints efficiently. One approach we might consider is the brute force method. Here, we enumerate all possible paths between node 1 and node n and then check if each path meets the restricted condition. While simple to conceptualize, this approach quickly becomes infeasible as the graph grows. Generating all possible paths can take exponential time, up to 2 to the power of n, and verifying each path adds further computational overhead. For large graphs, where n can be as high as 10 to the power of 4, this method is simply not practical. A more efficient solution involves using dynamic programming on the graph. The idea here is to count the number of restricted paths from each node to the last node using a combination of shortest path calculations and memoization. First, we compute the shortest distances from every node to node n, typically using Dijkstra's algorithm, as it is efficient for graphs with non-negative weights. Once we have these distances, we sort the nodes based on their distance to node n. This ordering ensures that we process nodes in a sequence that respects the restricted path condition. From there, we use dynamic programming to compute the number of restricted paths for each node, starting from node n and propagating backwards. Memoization allows us to avoid redundant calculations, significantly improving efficiency. The overall complexity combines the cost of Dijkstra's algorithm, sorting, and the DP traversal, making it well suited for large graphs. Another variation is to use a topological sort based on the shortest path distances. Here, the strict ordering of distances allows us to process nodes in a topological manner, counting restricted paths similarly to the DP approach. While this method achieves similar efficiency, it is less intuitive and harder to generalize for other types of problems. After evaluating the options, we chose to use the dynamic programming approach with Dijkstra's algorithm because it offers a good balance between clarity, efficiency, and scalability. The process begins with computing the shortest distances from all nodes to node n using Dijkstra, which is both fast and reliable for graphs with non-negative weights. Sorting the nodes by their distances ensures that we traverse them in the correct order to count restricted paths while adhering to the problem's constraints. Next, we use a DP table where DP, I, represents the number of restricted paths from node I to node n. Starting with the base case DP, n, equals 1, we propagate values backward through the graph, leveraging memoization to avoid redundant calculations. Since the number of paths can grow very large, we use modular arithmetic with a modulus of 10 to the power of 9 plus 7 to keep the results manageable. This strategy takes advantage of the shortest path distances to efficiently verify the restricted condition while ensuring that the computational steps remain scalable. Sorting the nodes eliminates cycles and guarantees a valid processing order, and dynamic programming ensures that no unnecessary work is repeated. This approach brings several trade-offs worth noting. Compared to the brute force method, it is exponentially faster, making it feasible for large-scale graphs. While the topological sort approach achieves similar performance, the dynamic programming method is more intuitive and easier to implement, especially when paired with Dijkstra's algorithm. In terms of complexity, the time cost is dominated by Dijkstra's algorithm, which runs in O, n plus m, log, n, where m is the number of edges. Sorting the nodes adds an O, n log, n, component, and the DP traversal through the graph is O, m. The overall time complexity remains efficient even for large inputs. The space complexity is O, n plus m, accounting for the graph representation and the DP table. By combining graph algorithms and dynamic programming, this method offers an optimal, scalable solution to the problem while maintaining clarity and reliability. In this problem, we are tasked with finding the number of restricted paths between two nodes in a weighted, undirected graph. The graph has n nodes, with node 1 as the starting point and node n as the destination. A restricted path is defined as a path where the distance to node n strictly decreases with each step. This condition makes the problem unique because it requires us to consider not just connectivity, but the structure of the shortest paths to node n. To solve this, we need to leverage three key components. First, we pre-compute the shortest distance from every node to node n using Dijkstra's algorithm, which is efficient for graphs with positive weights. Second, we traverse the graph to count valid paths that satisfy the restricted condition, and we do this using a modified DFS. Finally, to handle the computational complexity of counting paths in a graph with potentially up to 20,000 edges, we use dynamic programming with memoization. This ensures that once we compute the number of paths from a node, we reuse the result instead of recalculating it. For our data structures, we'll use an adjacency list to represent the graph, which is memory efficient for sparse graphs, and a priority queue to implement Dijkstra's algorithm for shortest path computation. To avoid redundant calculations, we'll also use a memoization table, implemented as an array DP, where DP, I, stores the number of restricted paths from node I to node n. The algorithm begins by parsing the input edges to create an adjacency list representation of the graph. This is done by iterating over the edges and populating a structure where each node points to its neighbors along with the corresponding edge weights. Once the graph is represented, we compute the shortest distances from all nodes to node n using Dijkstra's algorithm. We initialize a distance array where distance, n, is set to 0, and all other nodes are set to infinity. A priority queue is used to efficiently expand the node with the smallest current distance. The priority queue is initialized with node n at distance 0. As we process each node, we iterate over its neighbors and update their distances if a shorter path is found. These updated distances are then pushed back into the priority queue for further processing. This approach ensures that we explore nodes in order of increasing distance, which is the core principle behind Dijkstra's algorithm. As we continue processing the priority queue, for each node we pop, we check its neighbors. If traveling to a neighbor v through u results in a shorter distance than what we currently have for v, we update distance, v, and push this updated distance into the queue. Once the priority queue is empty, the distance array will contain the shortest distance from every node to node n. With the shortest distances computed, we move on to counting the restricted paths. This is done using a recursive DFS function. The function DFS node calculates the number of restricted paths from a given node to node n. The base case is straightforward. If the current node is n, there is exactly one path, which is the trivial path of staying at n. To avoid redundant calculations, we check the memoization table dp. If we've already computed the number of paths for the current node, we return the stored result. Otherwise, we initialize a counter total_paths to 0 and iterate over all neighbors of the current node. For each neighbor, we check the restricted condition: the distance to n must strictly decrease. If the condition is met, we recursively call DFS on that neighbor and add the result to total_paths. Once all valid neighbors have been explored, the total number of restricted paths from the current node is stored in the memoization table dp to avoid recalculating it in future calls. The function then returns this value. To compute the final result, we simply call DFS 1, which gives the number of restricted paths from node 1 to node n. Let's now analyze the complexity of our approach. Dijkstra's algorithm runs in O, n plus m, *log, n, where n is the number of nodes and m is the number of edges. For the DFS with memoization, each node is visited exactly once in the recursive calls, resulting in a time complexity of O, n. Combining these, the overall complexity of the solution is O, n plus m, *log, n, which is efficient given the constraints. Additionally, we account for edge cases. For example, we handle situations where node 1 cannot reach node n, in which case the result is 0. If the graph has only one node, the result is trivially 1 since 1 and n are the same. Finally, we ensure that the modulo operation is applied when summing paths to prevent integer overflow. In conclusion, this algorithm effectively combines Dijkstra's shortest path algorithm with a DFS-based dynamic programming approach to solve the problem efficiently. By pre-computing the shortest distances and leveraging memoization, we ensure that the solution is both optimal and scalable. This approach highlights the importance of breaking down complex problems into smaller, manageable components and using appropriate data structures to achieve the desired performance. With this method, we can confidently handle the constraints of the problem and produce the correct result while maintaining efficiency. To solve the problem, we begin by representing the graph using an adjacency list. This allows us to efficiently store the edges and their weights between nodes. For each edge in the input, we add its two endpoints along with the weight to the graph structure. Next, we implement Dijkstra's algorithm to calculate the shortest distance from the last node, labeled n, to every other node in the graph. We initialize a distance array with infinity for all nodes, except for the last node, which starts at 0 since the distance to itself is 0. A priority queue, or min heap, is used to process nodes based on the current shortest distance. As we pop nodes from the heap, we iterate over their neighbors and update the distances if we find a shorter path. If the updated distance to a neighbor is smaller than its current value, we push the new distance and the neighbor into the heap. This ensures that the shortest paths are propagated correctly throughout the graph. Now, to count the number of restricted paths, we use a depth-first search (DFS) approach with memoization. First, we define a modular constant, 10 to the power of 9 plus 7, to prevent overflow during calculations. We then create a recursive function, DFS, which takes the current node as input. If the current node is the last node, n, we return 1, as this represents a valid path. If the result for the current node has already been computed and stored in the memo dictionary, we simply return that value to avoid redundant calculations. Within the DFS, we iterate through the neighbors of the current node. For each neighbor, we check the condition that its shortest distance is strictly less than the distance of the current node. This ensures the path adheres to the restricted property. For valid neighbors, we recursively call the DFS function and accumulate the total paths, taking the modulus at each step. Finally, we store the result in the memo dictionary and return it. The function is initiated from node 1, and the total number of restricted paths is returned as the result. Here, we begin our Java implementation of the problem by first representing the graph using an adjacency list. We use a hash map to store each node as a key, with its value being a list of integer arrays. Each array represents a neighboring node and the weight of the edge connecting them. This structure allows us to efficiently look up all neighbors of a node. After initializing the graph, we populate it using the given edges, ensuring that each edge is added in both directions since this is an undirected graph. Next, we implement Dijkstra's algorithm to calculate the shortest distance from each node to the target node, which is node n. We initialize a distance array with a large value, integer.max_value, to represent infinity. The distance to the target node itself is set to 0, as it requires no traversal. We then use a priority queue to process nodes in order of their current shortest distance. Each element in the queue is an array where the first value is the distance and the second is the node. The priority queue ensures that the node with the smallest distance is processed first. While the queue is not empty, we retrieve and process the node with the smallest distance. If the current distance is greater than the recorded distance for the node, we skip it, avoiding unnecessary computation. Now, the loop continues by iterating through each neighbor of the current node. For each neighbor, we calculate the potential new distance by adding the weight of the edge to the current node's distance. If this new distance is smaller than the currently recorded distance for the neighbor, we update the neighbor's distance and add it to the priority queue for further processing. This ensures that we progressively refine the shortest distances to all nodes. Once Dijkstra's algorithm has computed the shortest distances, we move on to the second part of the solution, counting the restricted paths using depth-first search (DFS) with memoization. Restricted paths are those where the distance to the target decreases as we move along the path. To handle overlapping subproblems in the DFS, we use an integer array called memo to store the number of restricted paths starting from each node. The modulo constant, 1 times 10 to the power of 9 plus 7, is used to prevent integer overflow and ensure the result fits within the constraints. Finally, we initiate the DFS from node 1, passing in the graph, the distance array, the memoization array, and the modulo value. Within the DFS function, we first check if the current node is the target node. If it is, there is only one path, which is the node itself, so we return 1. If the result for the current node has already been computed and stored in the memo array, we simply return that value to avoid redundant calculations. Next, we iterate through all neighbors of the current node. For each neighbor, we check if its distance to the target is less than the distance of the current node. This condition ensures that the path adheres to the restriction of decreasing distances. If the condition is met, we recursively call the DFS function for the neighbor and add the returned value to the total paths, using the modulo operation to keep the result within bounds. After processing all neighbors, we store the total number of restricted paths in the memo array for the current node and return it. This completes the function, and ultimately, the solution returns the number of restricted paths starting from node 1. We start with an example where n equals 5, and the graph is defined by the given edges. First, we build the graph using an adjacency list. Each node is mapped to its neighbors along with the weights of the edges connecting them. For instance, node 1 connects to node 2 with a weight of 3 and to node 3 with a weight of 2. This adjacency list representation will help us efficiently traverse the graph. Next, we apply Dijkstra's algorithm starting from the last node, which is node 5. Initially, the distance to node 5 is set to 0, and all other distances are set to infinity. The heap is initialized with just node 5 at a distance of 0. We pop node 5 from the heap and update the distances to its neighbors. For example, the distance to node 4 becomes 5, and we push node 4 with this updated distance into the heap. Now, we process the heap further. We pop node 4 and update its neighbors. The distance to node 3 becomes 9, and the distance to node 2 becomes 11. Both nodes are pushed into the heap. We then pop node 3, updating the distance to node 1 to 11, which is pushed into the heap as well. At the end of Dijkstra's algorithm, the final distances from node 5 to all other nodes are recorded. With these distances, we move on to count the restricted paths using a depth-first search with memoization. Starting from node 1, we check its neighbors. For example, node 3 has a shorter distance to node 5 compared to node 1, so we recurse into node 3. Similarly, from node 3, we recurse into node 4, and from node 4, we reach node 5, which serves as our base case. As we backtrack, we memoize the results for each node, ensuring that redundant calculations are avoided. Ultimately, the number of restricted paths from node 1 to node 5 is 1. In a larger example with n equal to 4, we repeat the process. The graph is constructed from the given edges, creating an adjacency list. For instance, node 1 is connected to nodes 2 and 4 with weights 3 and 7, respectively. Next, Dijkstra's algorithm starts from node 4. Initially, node 4 has a distance of 0, and all other nodes are set to infinity. We pop node 4 from the heap and update its neighbors. The distance to node 3 becomes 2, and the distance to node 1 becomes 7. Both updates are pushed into the heap. This systematic updating ensures we calculate the shortest paths from node 4 to all other nodes. Continuing the algorithm, we pop node 3 from the heap and update the distance to node 2, which becomes 6. Node 2 is then pushed into the heap. Finally, we process the remaining nodes, and the distances stabilize as follows. Node 1 has a distance of 7, node 2 has 6, node 3 has 2, and node 4 has 0. With these distances finalized, we proceed to count the restricted paths using DFS with memoization. Starting at node 1, we explore its neighbors. For example, node 2 has a shorter distance to node 4 compared to node 1, so we recurse into node 2. From node 2, we proceed to node 3, and from node 3, we reach node 4, hitting the base case. As we backtrack, we memoize the results for nodes 3, 2, and 1. Once again, the total number of restricted paths from node 1 to node 4 is 1. In a highly connected graph with n equal to 3, we follow the same steps. The adjacency list representation is built, where node 1 connects to nodes 2 and 3 with weights 1 and 2, respectively. Similarly, other connections are established. Dijkstra's algorithm begins from node 3, setting its distance to 0. The heap is initialized with node 3 at a distance of 0. We pop node 3 and update its neighbors. The distance to node 2 becomes 1, and the distance to node 1 becomes 2. Both updates are pushed into the heap. After processing node 2 and node 1, the final distances are determined. Node 1 has a distance of 2, node 2 has 1, and node 3 has 0. To count restricted paths, we initiated DFS from node 1. Exploring its neighbors, we find that node 2 has a shorter distance to node 3 compared to node 1, so we recurse into node 2. From node 2, we proceed to node 3, where we hit the base case and return 1. As we backtrack, the results are memoized. Node 2 is assigned a value of 1, and node 1 is also assigned a value of 1. Thus, the number of restricted paths from node 1 to node 3 is 1. To analyze the time complexity of our solution, we need to break it into two main steps: Dijkstra's algorithm for computing the shortest distances and the DFS with memoization for counting restricted paths. First, let's consider Dijkstra's algorithm. We represent the graph using an adjacency list, which takes O(m) time to populate, where m is the number of edges. The core of Dijkstra's algorithm involves processing each node and examining all edges. Using a priority queue, updates to the shortest distances involve a logarithmic factor due to the heap operations. This means that for n nodes and m edges, the time complexity of Dijkstra's algorithm is O(n plus m asterisk log n). Now, moving to the DFS with memoization, each node is visited at most once thanks to memoization, and every edge is examined in the worst case. This results in a time complexity of O(n plus m) for the DFS traversal. The memoization ensures that repeated computations are avoided, keeping this step efficient. When combining the time complexities of both steps, we have Dijkstra's algorithm contributing O(n plus m asterisk log n, and the DFS with memoization contributing O(n plus m). Since Dijkstra's algorithm involves a logarithmic factor, it becomes the dominant term. Therefore, the overall time complexity of the solution is O(n plus m asterisk log n). Next, looking at space complexity, the graph representation as an adjacency list requires O(n plus m) space to store nodes and edges. The DIST array, which stores shortest distances, has a size of n plus 1, contributing O(n). The priority queue used in Dijkstra's algorithm can hold up to n nodes in the worst case, so it also requires n space. Lastly, the memoization dictionary used in the DFS can have an entry for each node, adding another n. Adding up these components, the overall space complexity is n plus m. Now, considering the best, average, and worst case scenarios, the best case occurs when all nodes are directly connected to the target node n and the graph is sparse, meaning it has very few edges. In this case, Dijkstra processes a minimal number of edges, and the DFS explores only relevant nodes, simplifying the time complexity to n asterisk log n. In the average case, the graph is moderately dense, with a number of edges m, and both Dijkstra and DFS process most nodes and edges. Here, the time complexity remains n plus m asterisk log n. The worst case occurs when the graph is fully connected, meaning it is dense and has n squared edges. Even in this case, Dijkstra processes all edges and the DFS explores all paths, but the time complexity remains bounded at n plus m asterisk log n, where m approaches n squared. When comparing the optimized solution to a brute force approach, the difference in efficiency becomes clear. A naive solution would attempt to enumerate all possible paths from node 1 to node n and check the restricted condition for each path. This process results in an exponential time complexity of k*2 to the power of n, where k is the number of valid paths. For large graphs, this is computationally infeasible. In contrast, the optimized solution leverages Dijkstra's algorithm to compute shortest distances efficiently in n plus m asterisk log n, and uses DFS with memoization to avoid redundant computations, ensuring that each node is processed only once. This reduces the complexity of the DFS to n plus m. As a result, the optimized solution is significantly more efficient and scalable, achieving an overall time complexity of n plus m asterisk log n, compared to the exponential time complexity of the brute force approach. Finally, to solidify the complexity analysis, let's look at the mathematical reasoning behind the big O complexity. Dijkstra's algorithm processes n nodes and examines m edges, with each operation involving a priority queue. This leads to a complexity of n plus m asterisk log n, where the logarithmic factor arises from heap operations. For the DFS, the linear complexity of n plus m comes from visiting each node and edge at most once. When summing these, the overall complexity is dominated by Dijkstra's n plus m asterisk log n, as the logarithmic growth rate of log n outpaces the linear terms. This confirms that the solution is efficient and well suited for large graphs. One of the most common mistakes in this problem is misunderstanding what restricted paths actually mean. Many assume it involves minimizing edge weights or the total path length, but that's not the case. A restricted path is defined by the property that the distance to the last node decreases at each step along the path. Misinterpreting this can lead to incorrect prioritization of nodes or edges in your solution. Another frequent mistake is skipping Dijkstra's algorithm for shortest path calculations. Since the edge weights in the graph can vary, using BFS instead of Dijkstra will produce incorrect results because BFS doesn't account for edge weights. Additionally, when counting paths, forgetting to apply modular arithmetic is a common pitfall. The number of paths can grow extremely large, and neglecting to take results modulo 10 to the power of 9 plus 7 can cause overflow or incorrect answers. Efficiency is another critical area. Using an unoptimized DFS or skipping memoization can lead to solutions that exceed time limits, especially given the problem's constraints of up to 10,000 nodes and edges. Lastly, errors in graph construction, like mishandling undirected edges, can result in incomplete or invalid graphs. Always ensure edges are added in both directions when building the graph representation. This problem is a great test of your ability to combine different techniques, particularly shortest path algorithms and dynamic programming. Recognizing this pattern is critical, as the solution requires first using Dijkstra's algorithm to compute shortest paths and then leveraging those results in a DP-based approach to count restricted paths. During interviews, you should be ready to discuss edge cases, such as graphs with only one node, disconnected components, or scenarios where all edges have the same weight. These conditions can help demonstrate your thoroughness in handling various inputs. Optimization is another key discussion point. Interviewers might ask why you chose Dijkstra over BFS or how you could further optimize your solution, such as using a priority queue for faster shortest path computations. To strengthen your understanding, it's helpful to explore related problems. For instance, LeetCode number 743, Network Delay Time, focuses on shortest path calculations with Dijkstra. LeetCode number 787, Cheapest Flights Within K-Stops, combines shortest path techniques with additional constraints, while LeetCode number 1631 and number 1514 involve variations of graph traversal with unique objectives. Studying these can sharpen your intuition for solving similar problems. When solving this problem, the optimal approach combines Dijkstra's algorithm with DFS and memoization. Dijkstra efficiently computes the shortest paths from the last node to all others, while DFS and memoization count restricted paths in a time-efficient manner. The trade-off here is the additional space required for memoization, and the approach also assumes a correct implementation of Dijkstra. An alternative is using the Bellman-Ford algorithm instead of Dijkstra for shortest path calculations. Bellman-Ford is simpler to implement but much slower for dense graphs, with a time complexity of O(n*)m. This makes it less practical for large inputs. Another less common approach is to use Floyd-Warshall to compute all pairs' shortest paths and brute force all possible paths to count restricted ones. While this method is conceptually straightforward and easy to debug, it's highly inefficient with a time complexity of O(n³), making it unsuitable for graphs with 10,000 nodes. This approach is only viable for very small graphs where performance constraints are less critical. Choosing the right method involves balancing simplicity, efficiency, and the constraints of the problem. Great job making it to the end. In this session, we tackled the problem step by step, combining graph algorithms and dynamic programming to find a solution. Remember, mastering shortest path algorithms like Dijkstra's is key for these types of problems. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!